Two-stroke diesel engines still power most of today's large ships, but the use of four-stroke engines for propulsion is increasing due to the flexibility about where they are fitted and the increased redundancy that a higher number of smaller engines can provide. Four-stroke diesel engines are usually used for electrical power generation. Diesel engine diagnosis is a tool which should help secure both the reliability of the diesel engine and its highest efficiency. It should be possible to assess the technical state of the engine parts without taking the engine apart, in order to prevent critical faults at sea and to have condition-based maintenance. The selection of the engine parameters we measure is based mainly on classification society rules, which define the scope of the engine monitoring. Engine monitoring can be considered as a simplified diagnosis, which follows this simple rule. As long as the critical engine parameters are within a certain range, we can assume that there is no direct danger of a critical fault. However, such basic monitoring does not support striving for maximum engine efficiency or the optimization of maintenance, so a more detailed diagnosis can bring significant benefits. The engine parameter values depend on both the condition of the engine and the operating conditions. The operating conditions include ambient factors like ship draft, seawater state, air pressure and temperature, as well as the chosen parameters, such as a requested ship speed or given electrical load. It should be clear that most engine parameters change significantly when the engine order telegraph position is changed. The best diagnostic parameters to use are measured engine values, which fulfill the following requirements. Their value depends not only on the operating conditions, but also to a great extent on the technical state of the engine. They help us to avoid the most serious faults. They help us to optimize the maintenance process, and they can be measured with the available engine equipment. The diagnostic parameters most commonly used for evaluation of engine performance are engine RPM, engine power, load index, engine torque, and specific fuel consumption calculated over a long enough period of time. The diagnostic parameters used for the evaluation of combustion are indicator diagrams, mean indicated pressure, the exhaust gas temperature after each cylinder, the compression pressure in each cylinder, and the maximum pressure in each cylinder. The diagnostic parameters used for the evaluation of a turbocharger are scavenge air pressure, turbocharger RPM, exhaust temperature before the turbocharger, exhaust temperature after the turbocharger, air pressure drop at the air filter, air pressure drop at the air cooler, the exhaust pressure after the turbocharger, known as the counter pressure, and the cooling water temperature difference at the air cooler. The diagnostic parameters used for the evaluation of engine cooling are cooling water temperature after each cylinder, cooling water temperature at the inlet to the engine, and the piston cooling oil temperature at the inlet to the engine. The diagnostic parameters used for evaluation of engine lubrication are main bearing temperatures if available, lubricating oil temperature before the engine, water content in the lubricating oil, lubricating oil pH, and the lubricating oil viscosity. As we have said, the value of many diagnostic parameters depends both on the current operating conditions and on the technical state of the engine. Because of this, we need to compare the values of diagnostic parameters not just with their previous values, but rather with their reference values, which can be read out from sea trial information, sometimes called model diagrams. Different conditions should be used as independent variables for different diagnostic parameters, because we can use them to evaluate different engine components. Model diagrams are usually based on the sea trial or test bed results. Another type of model diagrams are indicator diagrams, showing the pressure in the combustion chamber as a function of the piston stroke, or as a function of the crank angle. Parameter deviation is the difference between the actual value of the diagnostic parameter and its reference value, which can be read from the relevant model diagram. Ideally, the deviation should depend only on the engine condition, but in reality, it may still change with operating conditions, even if the engine condition is more or less the same. Operating conditions vary all the time, so we need to observe the deviation behavior within a long enough time period, like days, weeks, or even months. To do that, parameter deviations should be recorded continuously, either manually or automatically. The graphs showing the behavior of the deviation are called time-based deviation charts. It is sometimes difficult to precisely set the acceptable range of allowable deviations, so it is usually necessary to establish the trend of the changes. This can be done both visually, when looking at the time-based deviation graphs, or mathematically, by watching so-called trend lines in a spreadsheet. Sometimes the engine manufacturer defines the acceptable range of changes and how many deviations going outside the range can be accepted. Different engine faults can sometimes give the same deviation trend. Additional checks therefore have to be applied in order to exclude the less probable causes. Occasionally, only engine disassembly can deliver the final answer. A diagnostic logic which can be applied to searching for faults is described later in this module. We will look at three specific engine performance problems: engine overload, high specific fuel consumption, and excessive engine vibrations. Engine overload is frequently caused by trying to drive the ship hard through rough seas with a high setting of the requested engine RPM. Engine overload is often signaled by the engine monitoring system, but continuous observation of the location of the operating point should be applied in order to avoid such a situation. Positioning the operating point requires measurement of the engine RPM and torque, which can then be placed as coordinates on the original performance graph, delivered by the engine manufacturer. To establish the trend in specific fuel consumption, we first need to compare the measured value with a model diagram value for the same engine power, because fuel consumption will vary with engine load. We can then plot the deviation over a period of time, possibly weeks, because some external factors, like tide or weather conditions, may affect individual readings in the short term. If the specific fuel consumption is higher, it shows that there is a lower overall engine efficiency, and this should lead to further diagnostic research to find the cause. Some engine vibrations are quite normal, especially when starting the engine or sailing in rough seas. Most engine faults can be classified into two categories: combustion faults and mechanical faults. For combustion faults, vibration-based condition monitoring can be further divided into two types. One is based on the translational acceleration signals measured on the engine block or the cylinder tightening bolts, while the other is based on the torsional vibration signal of the crankshaft, derived from a torque meter. To use these signals, it is usually necessary to have the appropriate software for data analysis. Even then, faults cannot always be automatically diagnosed from the analyzed vibration signals. So any deviation should start a further search to try and find the exact fault location. At its simplest level, the frequency of vibrations is usually the major clue to where the fault lies. The vibrations will be at the same frequency or have components at multiples of the frequency of the faulted part. As a simple example, very high frequency vibrations are most likely to come from high-speed components, such as those in the turbocharger. Very low frequency vibrations tend to be associated with the shafting system. In this chapter, we are going to look at typical problems with engine combustion. The symptoms of these include dark smoke from the funnel, increasing positive deviation of the mean exhaust gas temperature, increasing deviation of the exhaust gas temperature after a single cylinder, increasing negative deviation of the compression pressure in a single cylinder, increasing negative deviation of the maximum combustion pressure in a single cylinder, or increasing negative deviation of the mean indicated pressure, MIP, in a single cylinder or group of cylinders. Dark smoke from the funnel usually means that there is not enough air for combustion. It can appear in the following situations: when the engine starts, during a rapid load increase, for instance when maneuvering, or in rough seas due to abnormal engine loads. Dark smoke at stable engine loads can be caused by a fault in the turbocharging system, so the turbocharging checks specified later in this module should be applied. When evaluating the exhaust gas temperatures, the first step should be to compare the actual value of the average exhaust temperature with the average value from the model diagram for the same engine power and record the deviation. This should be done at least once a week. An increasing positive deviation of the average exhaust gas temperature can be caused by the following problems: high inlet temperature of the cylinder cooling water, low inlet pressure of the cylinder cooling water, high inlet temperature of the oil cooling the pistons, low inlet pressure of the oil cooling the pistons, or not enough combustion air, which can be detected by the turbocharging checks specified later in this module. When evaluating the exhaust gas temperatures after each cylinder, the first step is to compare the actual value with the average exhaust temperature after all cylinders at the same moment in time. The deviation for each cylinder can then be recorded, and this should be done at least once a week. Some differences in the exhaust temperatures between units may be quite normal, but changes in the observed deviations tell us that something has changed and can be used for engine condition diagnosis. An increasing positive deviation of the exhaust gas temperature after a single cylinder can be generated by the following problems: late combustion, caused by the wrong injection timing or by a worn fuel injector valve, which can be identified using an indicator diagram. Late combustion, caused by low compression in an untight cylinder, which can also be identified using an indicator diagram. Or a leaking exhaust valve, which can be identified by an increasing negative deviation of the compression pressure, as described later in this module. When evaluating the compression pressure in a cylinder, compare the actual value of the compression pressure with the value from the model diagram for the same scavenge air pressure, and record the deviation. This should be done at least once a week. An increasing negative deviation of the compression pressure in a cylinder can be caused by the following problems, which can usually be seen during a scavenge port inspection. Blocked cylinder inlet ports, wear of the piston rings or the cylinder, clogged or burned out piston rings. When evaluating the maximum combustion pressure in each cylinder, compare the actual value with the average maximum combustion pressure in all cylinders at the same moment in time. The deviation for each cylinder can then be recorded, and this should be done at least once a week. Some differences in the maximum combustion pressure between units may be quite normal, but changes in the observed deviations tell us that something has changed and can be used for engine condition diagnosis. An increasing negative deviation of the cylinder maximum combustion pressure can be caused by the following problems. A low compression pressure, which should be eliminated first, as described earlier in this module. Delayed combustion, which can be caused by the wrong injection timing or worn injector nozzles. This problem can be observed on the indicator diagram. A decreased quantity of fuel injected, which can be caused by a worn plunger in the fuel pump. This can be confirmed by checking the mean indicated pressure, as described later in this module. When evaluating the mean indicated pressure, MIP, in each cylinder, compare the actual value with the average mean indicated pressure in all cylinders at the same moment in time. The deviation for each cylinder can then be recorded, and this should be done at least once a week. Some minor differences in the mean indicated pressure between units may be quite normal, but changes in the observed deviations tell us that something has changed and can be used for engine condition diagnosis. An increasing negative deviation of the cylinder maximum combustion pressure can be caused by the following problems. A low compression pressure, which should be looked for first, as described earlier in this module. Delayed combustion, which should also be eliminated first, as described earlier in this module. A decreased quantity of fuel injected, which can be caused by a worn plunger in the fuel pump. This can be confirmed by checking the indicator diagram first, and if this is the cause, then the fuel pump should be overhauled. The typical symptoms of turbocharging problems are increasing negative deviation of the scavenge air pressure, increasing deviation of the turbocharger speed, either positive or negative, increasing positive deviation of the air pressure drop at the air filter, increasing positive deviation of the air pressure drop at the air cooler, increasing negative deviation of the cooling water temperature at the air cooler, or increasing cylinder block temperature near the scavenge box. When evaluating the scavenge air pressure, first compare the actual value of the scavenge air pressure with the value from the model diagram for the same engine power, and record the deviation. This should be done at least once a week. An increasing negative deviation of the scavenge air pressure can be caused by the following problems. A dirty air filter, which should be eliminated first, as described later in this module. A faulty or dirty turbocharger, which can be identified using the checks described later in this chapter. A dirty exhaust duct after the engine, which can be identified by checking the exhaust pressure after the turbocharger. When evaluating the turbocharger speed, first compare the actual value of the turbocharger speed with the value from the model diagram for the same scavenge air pressure, and record the deviation. This should be done at least once a week. An increasing negative deviation of the turbocharger speed can be caused by the following problems: a corroded turbocharger nozzle ring or turbine blades, or too large a clearance between the turbine blades and the shroud or cover. We have already seen that turbocharger speed should be referred to the scavenge air pressure on the model diagram. However, in this case we see a positive deviation of the turbocharger speed on the time-based deviation chart. An increasing positive deviation of the turbocharger speed can be caused by the following problems: a dirty air filter, which should be eliminated first, as described later in this module. A dirty air cooler, which should be eliminated first, which will also be described later in this module. A dirty turbocharger, air side or gas side, which should be eliminated by washing both sides, in accordance with the engine manual. When evaluating the air pressure drop at the air filter, first compare the actual value of the air pressure drop with the value from the model diagram for the same scavenge air pressure, and record the deviation. This should be done at least once a week. An increasing positive deviation of the air pressure drop at the air filter can be caused by a dirty air filter, which should be cleaned in accordance with the engine manual. When evaluating the air pressure drop at the air cooler, first compare the actual value of the air pressure drop with the value from the model diagram for the same scavenge air pressure, and record the deviation. This should be done at least once a week. An increasing positive deviation of the air pressure drop at the air cooler can be caused by a dirty air side of the air cooler, which should then be cleaned in accordance with the engine manual. When evaluating the cooling water temperature difference at the air cooler, compare the actual value of the cooling water temperature difference with the value from the model diagram for the same scavenge air pressure, and record the deviation. This should be done at least once a week. An increasing negative deviation of the cooling water temperature difference can be caused by a dirty water side of the air cooler, which should then be cleaned in accordance with the engine manual. The approximate temperature of the cylinder block surface near the scavenge box can be measured with the use of an infrared camera, or estimated by putting the palm of the hand close to, but not touching, the cylinder block. The measured temperature should then be compared with other cylinders. An increasing cylinder block temperature near the scavenge box, especially when combined with an increase in the exhaust gas temperature and cooling water outlet temperature, can be a symptom of a scavenge box fire. Such a fire is usually caused by worn piston rings or an excessive quantity of cylinder oil. When a scavenge box fire is suspected, the engine load should be decreased immediately, and CO2 extinguishing should be applied in accordance with the engine manual. A typical symptom of a problem with the engine is an increasing positive deviation of the cooling water temperature difference at the cylinder. When evaluating the cooling water temperature difference at the cylinder, the first step should be to compare the actual value of the cooling water temperature difference with the value from the model diagram for the same engine power, and record the deviation. This should be done at least once a week. An increasing positive deviation of the cooling water temperature difference at a cylinder can be caused by several problems. A crack in the cylinder liner, which can be accompanied by bubbles in the cooling water expansion tank. A crack in the cylinder head, which can also be accompanied by bubbles in the cooling water expansion tank. An obstacle in the cylinder liner, or the cylinder head cooling space. In this case, there are no bubbles in the cooling water expansion tank. Typical symptoms of a problem with engine lubrication are increasing positive deviation of the main bearing temperatures, high water content in the lubricating oil, low pH of the lubricating oil, low viscosity of the lubricating oil, high contamination or low dispersancy of the lubricating oil. The value of each main bearing temperature should be compared with the limiting value, and an alarm should be activated when it reaches this limit. The limiting value depends both on the main bearing material and on the location of the temperature sensor. An increasing positive deviation of a main bearing temperature can be caused by several problems. A seizure process in the bearing, which can be caused by material failure, sudden load increase, or obstructed oil flow. An obstructed flow in the crankshaft drillings caused by lubricating oil impurities. A cylinder mechanical overload caused by an excessively high maximum combustion pressure, or corrosion of the bearing. Remember that seizure of a main bearing can lead to the destruction of the bearing and a main engine emergency stop. The water content can be tested on board with equipment similar to that shown, but it can also be monitored continuously by a sensor installed on the inlet pipe of the lubricating oil. An increasing water content in the lubricating oil can be caused by several problems. Insufficient or faulty operation of the lubricating oil separator. A cooling water leak into the cylinder because of a crack in the cylinder liner or cylinder head. Excessive water condensation in the charge air after the cooler. This usually happens when the air humidity is high and the scavenge air temperature is low, so that the dew point is reached. This can be confirmed by opening the drain valve in the scavenge box. A worn or broken stuffing box can allow water leaking from the scavenge box into the engine crankcase. Remember that high water content in the lubricating oil can lead to bearing corrosion, poor lubrication, and bearing seizures. The lubricating oil pH can be tested with pH testing strips similar to these. Low pH of the lubricating oil can be caused by several problems. An increased quantity of acidic combustion products because of a high sulfur content in the fuel, or a low TBN of the cylinder oil. Or a worn or broken stuffing box, allowing combustion products to get into the engine crankcase. Low pH of the lubricating oil is a serious problem, since it can lead to bearing corrosion. The viscosity of the lubricating oil can be tested by a comparison of the oil flow speed, using a flow stick similar to this one. Low viscosity of the lubricating oil can be caused by several problems. Unburned fuel oil leaking past the piston rings to the stuffing box and then further through an untight stuffing box into the crankcase. A high water content in the lubricating oil, or by oil deterioration with age or by contamination. Remember that low viscosity of the lubricating oil can lead to severe engine damage. Contamination and dispersancy of the lubricating oil can be tested using a so-called spot test. In this test, a drop of oil is put on blotter paper and then dried for a few hours. The dry spot is then compared with the example spots available, which allows us to gauge the insoluble components in the oil. High contamination of lubricating oil is usually caused by ineffective oil filtering or insufficient cleaning in the lubricating oil separator. Contaminants in the oil can block the oil flow in small clearances and disturb hydrodynamic lubrication. Low dispersancy of the lubricating oil is usually caused by aging of the oil. Dispersancy of the lubricating oil is necessary to divide larger sized deposits into tiny particles, which can then be carried evenly throughout the bulk of the oil and later removed by filtration.